For a 400 amp residential service using 3/0 conductors in parallel, the grounding electrode conductor size is determined by referencing the applicable electrical code. To accurately determine the grounding electrode conductor size, firstly, we need to identify the size of the service entrance conductors. In this scenario, we have 3/0 conductors in parallel. Since there are two 3/0 conductors per phase, we need to determine the equivalent ampacity of these parallel conductors. To do this, we first find the ampacity of a single 3/0 conductor. The ampacity of 3/0 copper conductors depends on the insulation type and temperature rating. Assuming we are using typical 75 degrees Celsius rated conductors, a 3/0 copper conductor has an ampacity of around 200 amps. Secondly, since we have two 3/0 conductors in parallel per phase, the total ampacity per phase is 2 times 200 amps, which equals 400 amps. The grounding electrode conductor size must be appropriate for a service of this size. Thirdly, we reference the appropriate table in the electrical code, such as Table 250.66 in the National Electrical Code, NEC, to determine the minimum size of the grounding electrode conductor. This table provides the required grounding electrode conductor size based on the size of the service entrance conductors. For a copper service entrance conductor size of 400 amps, Table 250.66 typically requires a grounding electrode conductor to be a minimum of 1/0 copper. Therefore, in this case, a 1/0 copper grounding electrode conductor is suitable. Fourthly, it is important to consider the type of grounding electrodes used. Common grounding electrodes include metal underground water pipes, concrete encased electrodes, and ground rods or ground rings. The size of the grounding electrode conductor may vary based on the type of grounding electrode. For example, if using ground rods, there may be specific requirements for the grounding electrode conductor size based on the rod material and installation depth. Fifthly, it is necessary to ensure that the grounding electrode conductor is properly connected to the grounding electrode. The connection must be made using approved methods and connectors to ensure a reliable and low impedance path to ground. Proper installation techniques are essential for effective grounding. Sixthly, consider any local amendments or requirements that may supersede the National Electrical Code. Local jurisdictions sometimes have specific rules that must be followed. Always check with the local authority having jurisdiction, OJ, to ensure compliance with all applicable regulations. Seventhly, it is crucial to understand the purpose of the grounding electrode conductor. The grounding electrode conductor connects the service equipment, such as the neutral bus in the service panel, to the grounding electrode. This connection ensures that the electrical system is properly grounded, providing a path for fault current to return to the source and helping to prevent electrical shock hazards. Eighthly, let's talk about the material of the grounding electrode conductor. While copper is a common choice, aluminum conductors are also permitted under certain conditions. If using aluminum, the grounding electrode conductor size must be adjusted according to Table 250.66. Aluminum conductors generally require a larger size than copper conductors for the same ampacity. Ninthly, consider the physical protection of the grounding electrode conductor. The conductor should be protected from physical damage to maintain its integrity. If the conductor is exposed to physical damage, it should be installed in conduit or otherwise protected. Tenthly, it is essential to perform regular inspections and maintenance of the grounding system. Check the grounding electrode conductor and connections for corrosion or damage. Ensure that the grounding electrode is still effective and that the grounding system is functioning as intended. 11thly, remember that grounding is a critical aspect of electrical safety. Proper grounding helps to minimize the risk of electrical shock, fire, and equipment damage. Always follow the electrical code and use qualified electricians for electrical work. 12thly, let's clarify some misconceptions about grounding. Grounding does not prevent electrical shock under all circumstances. It primarily provides a low impedance path for fault current to flow back to the source, which then causes the overcurrent protective device, such as a circuit breaker or fuse, to trip and energize the circuit. 13thly, let's discuss the difference between grounding and bonding. Grounding connects the electrical system to the earth, while bonding connects non-current carrying metal parts together to create an electrically conductive path. Both grounding and bonding are essential for electrical safety. 14thly, when selecting the grounding electrode conductor, it's important to consider the overall design of the electrical system. The grounding system should be designed to effectively handle fault currents and provide a stable reference point for the electrical system. 15thly, remember to properly label the grounding electrode conductor and the grounding electrode. This helps to identify the grounding system components and ensures that they are not inadvertently disconnected or damaged. 16thly, let's discuss the use of supplemental grounding electrodes. In some cases, it may be necessary to install supplemental grounding electrodes to improve the effectiveness of the grounding system. This is particularly important in areas with high soil resistivity. 17thly, be aware of the requirements for the minimum length and depth of ground rods. Ground rods must be installed to a certain depth to ensure that they are in contact with the earth and provide an effective grounding path. The electrical code specifies the minimum length and depth requirements. 18thly, when using a metal underground water pipe as a grounding electrode, it's important to ensure that the pipe is electrically continuous and that it is in direct contact with the earth. Plastic pipes or insulated couplings can interrupt the grounding path. 19thly, be familiar with the requirements for the size and type of grounding electrode clamps. Grounding clamps must be approved for the specific application and must be compatible with the materials of the grounding electrode conductor and the grounding electrode. 20thly, it is crucial to understand the importance of equipotential bonding. Equipotential bonding involves connecting all metal parts within a certain area to create a common electrical potential. This helps to prevent voltage differences that can cause electrical shock hazards. 21stly, let's discuss the use of ground fault circuit interrupters, GFCIs. GFCIs are designed to protect against electrical shock by detecting small ground faults and quickly de-energizing the circuit. GFCIs are required in many areas, such as bathrooms, kitchens, and outdoor locations. 22ndly, remember to properly torque all electrical connections, including grounding connections. Loose connections can cause overheating and arcing, which can lead to electrical fires. Use a torque wrench to ensure that connections are tightened to the specified torque values. 23rdly, let's discuss the requirements for the installation of surge protective devices, SPDs. SPD are designed to protect against voltage surges caused by lightning or other events. SPD should be installed at the service entrance and at other critical locations in the electrical system. 24thly, be aware of the potential for corrosion in grounding systems. Corrosion can degrade the grounding connections and reduce the effectiveness of the grounding system. Use corrosion-resistant materials and coatings to protect against corrosion. 25thly, when working on electrical systems, always follow safe work practices. To energize the circuit before working on it, use appropriate personal protective equipment (PPE) and follow lockout/tagout procedures. 26thly, it is important to stay up to date with the latest changes to the electrical code. The electrical code is updated regularly to reflect new technologies and best practices. Attend training courses and read industry publications to stay informed. 27thly, let's discuss the use of isolated ground receptacles. Isolated ground receptacles are designed to reduce electrical noise in sensitive electronic equipment. They have a separate grounding conductor that is isolated from the normal equipment grounding conductor. 28thly, remember to properly support and secure all electrical conductors, including grounding conductors. Conductors should be supported to prevent strain on connections and to protect against physical damage. 29thly, be aware of the requirements for the installation of grounding bushings and bonding jumpers. Grounding bushings and bonding jumpers are used to provide a low impedance path for fault current to flow back to the source. 30thly, it is crucial to understand the importance of the neutral conductor in the electrical system. The neutral conductor carries the unbalanced current back to the source and provides a reference point for the voltage. The neutral conductor must be properly sized and installed to prevent voltage drops and other problems. 31stly, let's discuss the use of high-resistance grounding systems. High-resistance grounding systems are used in industrial applications to limit fault current and reduce the risk of arc flash. These systems use a resistor to limit the ground fault current to a low level. 32ndly, remember to properly document all electrical work, including the grounding system. Keep records of the grounding electrode conductor size, the grounding electrode type, and the installation methods used. This documentation can be helpful for future maintenance and troubleshooting. 33rdly, be aware of the potential for stray voltage. Stray voltage is a small voltage that can be present on metal surfaces due to inductive coupling or other factors. Stray voltage can be a nuisance or even a safety hazard. 34thly, when using a ground ring as a grounding electrode, it's important to ensure that the ring is buried at the proper depth and that it is in continuous contact with the earth. The electrical code specifies the minimum depth and size requirements for ground rings. 35thly, be familiar with the requirements for the installation of grounding electrodes in concrete. Concrete can be corrosive to some metals, so it's important to use corrosion-resistant materials and coatings. 36thly, it is crucial to understand the importance of harmonics in electrical systems. Harmonics are distortions of the voltage and current waveforms that can cause overheating and other problems. Harmonics can be mitigated by using filters or other techniques. 37thly, let's discuss the use of power quality meters. Power quality meters can be used to measure voltage, current, harmonics, and other parameters in the electrical system. This information can be helpful for troubleshooting and improving the performance of the electrical system. 38thly, remember to properly train all personnel who work on electrical systems. Electrical work can be dangerous, so it's important to ensure that workers are properly trained and qualified. 39thly, be aware of the potential for electromagnetic interference, EMI. EMI can interfere with the operation of electronic equipment. Shielding and filtering can be used to reduce EMI. 40thly, it is crucial to understand the importance of preventive maintenance in electrical systems. Regular inspections and maintenance can help to prevent problems and extend the life of the electrical system. So based on table 250.66, a 1/0 copper grounding electrode conductor is typically required for a 400 amp service supplied by 3/0 copper conductors in parallel. However, always consult the latest edition of the NEC and local amendments for the most accurate and up-to-date requirements.